super happy to introduce our next person. This is Steve Wallace. He's one of my coworkers. He will be presenting Improving Routing Security for Global Research and Education. Steve is Director of Routing Integrity at Internet2 and has traveled from Bloomington, Indiana to join us today. Within Internet2, he's better known as Mr. Linda Roos. His wife is more famous than he is in our community. So he's here standing on his own today. He might need a little extra audience support for that.
Thanks, Vic.
Take it away, Steve.
Can you guys hear me? Can you hear me? Okay, good. So I'm curious, how many of you support research and education networks? So a fair amount, okay. So a little bit of geezer trivia. 27 years ago, Internet2 did its first demonstration of its nationwide R&E backbone in this hotel. And we had an OC12 packet over sonnet into the hotel to do some demos. So it was, when I got to the hotel, I'm like, I've been here before, and I had to look it up to see what that was about. So I'm going to tell a story about how some network research is getting translated into tools to improve research networks. This is a project with Internet2 and CADA. The part that's translating these into operational tools we call root beer, routing operations, observational technology, building to enable education and research. I think Casey Claffey came up with that acronym. So here we go. So research education networks, they're specialized infrastructure. They're meant to build gaps. They're built to meet the mission needs of researchers that need to exchange large data sets over long distances. The network needs to preserve end-to-end connectivity for the most part. That makes it impractical to use commercial CDNs. The primary focus for R&E networking is high-speed, low-latency connectivity among members. But the members may need to arrange their own commodity transit. To give you a sense of the scale of the interconnected R&E infrastructure, it interconnects facilities in 104 countries. There are roughly 2,700 origin ASs that are originating v4. We're going to keep this to v4 for right now. And there are roughly 12,000 IPv4 prefixes that represent these networks. So how do the members of this infrastructure connect? In this example, ASA at the top and ASB at the bottom are members of this infrastructure. We'll call it ASA a university in California. And a university in California would typically connect to Scenic as their regional network that supports research and education. And then Scenic would connect to Internet2, the nationwide backbone that interconnects the regional networks like Scenic. Scenic also connects to a transit provider, and we'll just say it's Lumen in this example. ASB might be a university in New York State, and NYSERNet is a regional network in New York State that meets their needs. And NYSERNet, like Scenic, connects to Internet2. And ASB may have a direct connection to a provider, and let's just say it's Lumen in that case as well. So ASB is going to receive two routes to ASA, one from Lumen, one from NYSERNet. The shorter path is going to be the one from Lumen. So what does ASB do? Well, for ASB to reliably pick the R&E path, they're going to have to set a higher local pref for routes that they learn from that peer. But do they? And so this was part of the research that we did, trying to answer this question. Do these networks actually do this? So BGP is an information hiding protocol. ASA can't really tell what ASB is going to do because it doesn't really have a downstream view of the BGP policy ASB is going to implement. Well, you think, well, we could go to different public views of BGP, But when you look at the 2,700 ASNs within this environment, roughly 1% are covered by services like Route Views and Ripe RIS, and it's better for Ripe Atlas, but it's still less than 10%. So we thought about how could we measure this globally, and we needed a system where we could originate routes and control their properties, and then we also needed to measure the global effect of these announcements, and we needed to do it in such a way that we didn't have to put infrastructure in these 2,700 ASs or 12,000 prefixes. So all we assumed was there would be an IP address within these ASs, or several IP addresses, that would respond to a ping. So we built a measurement system. It's dual homed. It has a connection to the R&E infrastructure, and it has a connection to the commodity infrastructure. And it announces the routes differently. So it has a /24, which is its sort of loop back in the source of the ping packets. And they're announced out the R&E infrastructure with one origin AS and out the commodity infrastructure with a different origin AS. And so if we're trying to test ASB's policy, ASB is going to see two routes. They're going to see one from their commodity and they're going to see one from R&E. If we send a ping to ASB and we see it come back on the R&E connection, then maybe they're local prefing R&E. And if we see it come back on commodity, maybe they're not. So how do we tell if they really are or not? Well, we ran a series of tests. We ran 9 tests. We took hour breaks between each test. Each test was pinging, I think, 3 to 4 theoretically responsive IP addresses within each one of the 12,000 prefixes. Each test took about 8 minutes to run. And so the first test, we prepended the announcements to the R&E network by 4 times. And so if responses came back over the R&E network, you could be relatively assured that local pref was overriding the AS path difference. And we varied the prepending through each test. So we started out with 4 prepends on R&E, 3, 2, 1, then none, and then we ramped them up on commodity. And you have some assurance if we're prepending commodity 4 times, and it's still picking commodity, that maybe they're local prefing commodity instead of R&E. So what did we find? Well, about 80% of the responsive hosts that we pinged in the 12,000 prefixes always returned over R&E. So for the most part, these networks are kind of doing what we thought they would do. 7% were always picking commodity, which is interesting. And this may be unintentional on their part, or maybe it is intentional. And then we would see things switch from commodity to R&E or R&E to commodity as we varied the lengths. And those are cases where it's not local pref that's doing this in either direction. They're basing this on AS path changes. So we authored a paper with Kata describing these tests in detail, how we ran the tests. We also ran them from the Internet 2 perspective, but we also ran them from SurfNet. So we extended a virtual interface of the measurement device into SurfNet to see if we did the test from there, would the results be the same? And the results are virtually identical. So the paper was accepted at the IMC in October, and Matthew Lucky did a presentation there, and the paper's available. So now I'm going to talk about the project to turn sort of what we learned and the capabilities we created for the paper into something to improve routing security for the R&E environment. Well, we built this prototype thing to investigate the local pref. We call it the local pref probe. but it's, we built it to do the research, not to be an operational thing that we're using on a regular basis. We realized there are other security relevant properties that we could investigate with this infrastructure, and we're now building an operational system to support R&E routing policy inferences, and this will be hosted by Internet 2, and this is being supported in part by the National Science Foundation. So part of what Root Beer is doing, it's putting systems in place to identify problematic routing. And R&E networks prefer routes from other R&E networks. At least 80% of them do. 80% of them local pref, the routes they receive from R&E. And this sets up kind of a dangerous situation. A member in this community, if they leak commodity routes into R&E, that can attract traffic they might not be prepared for. If a member leaking R&E routes into commodity, a member leaking RE routes into commodity can result in traffic across R&E infrastructure that should use commodity. And Anycast is a really special case. A member announcing an Anycast prefix into R&E can attract traffic best directed to other Anycast instances. These are not theoretical problems, unfortunately. We wrote a blog post in 2004 outlining specific examples of these. So there was, in March of 2024, a network in South America, an R&E network, leaks commercial routes into the R&E infrastructure. And remember, the R&E infrastructure tends to local pref those routes. And among the routes that they leaked were Cloudflare routes. And so this showed up in sort of the networks that interconnect them with the rest of R&E. And for a while, much of Europe, Asia, and North America were sending all their Cloudflare traffic and other traffic to South America. And it was quite impactful. In August of 2024, an R&E member in the Middle East leaked routes into the commercial internet provider. And it's not uncommon for networks that connect to this infrastructure to send out more specifics, just in case you're not using local pref, to ensure that their traffic is returned over the R&E infrastructure. So in this case, I know of a particular school in Texas that was sending, they deaggregated their /16 into a couple of 17s, and they were announcing those to the R&E infrastructure, and that was all good. This ensured that traffic was returning to them over R&E. Well, when this leak occurred, all of a sudden, the longest prefix match is via the Middle East. And the Middle East, this particular institution had a 1 gig connection. So, very impactful. Those examples were from a couple years ago, but we had a nice example in January this year. This was a V6 prefix, a Microsoft V6 prefix that was leaked by a network in Asia to Internet 2. And then we were essentially announcing it back to CERNET, which is the Chinese research and education backbone. And so for a while, we were seeing, and not just traffic from CERNET, but CERNET was the highest volume source. We were seeing CERNET traffic to Microsoft that was coming across the Pacific and then back across the Pacific due to this route leak. And this is one of those things that we found this out because somebody phoned us up and said, there's a problem, can you look into it? So we'd like to prevent, detect and prevent these route leaks. So in the US, our Internet 2's direct customers, we actually filter prefixes. So if you're a regional network like Scenic in California and you add a new school and you want Internet 2 to accept that route, you have to tell us you want us to accept the route and we'll update a filter facing that peering session. But it's generally been the case for at least 25 years that the International peering of RNE networks don't filter much. I mean, typically you'll see bogon filtering, you'll see peer lock, you'll see those kinds of things. But this infrastructure has a history of supporting mutual transit on all of these connections. So unlike a normal peering connection, they're typically exchanging all of their routes, all of their RNE routes. So, and this creates a nice resilient network, but does create other challenges, especially with filtering the routes. So part of what we're doing with root beer is we're building a system to actively maintain a public filter. And this public filter, hopefully, will be a good representation of all the prefixes that belong to the global RNE environment. And Internet 2 will use that filter to ensure that non-RNE routes are not being accepted from its international peers. And hopefully that will become a resource for other international peers to use the same filter. By using this kind of filter, we preserve the mutual backup or mutual transit capability, but at the same time reduce the chance of a commercial network being leaked. Okay, getting back to the test instrument we built, the local pref probe, in sort of thinking about the research that we did, we realized that instead of just probing the RNE prefixes, we could learn more if we probed all routed prefixes. And maybe we could do that every day. So send out ping packets to a few responsive hosts in every prefix that's announced on the internet, and we could learn something from that. So we might be able to learn when a member is leaking commodity routes into the RNE network. So here's an example. So I said that with Internet 2's direct customers, we filter those routes. We also see a pre-policy version. We keep track of the routes that are announced to us that we don't accept, that these routes are not permitted by the prefix list. And that could be for a number of reasons. It could be that something changed in the regional network and they just didn't let us know. They want us to start accepting this route. Or it could be a route leak that we're seeing. Fortunately, we're not propagating it, but we're actually seeing it happen. So if we're probing all of these prefixes, including the ones we're not accepting, and when we send a probe to a prefix that's one we're not accepting, but somebody's trying to announce it to us, and if its return is over the commodity path, then it's likely that that is actually a leaked route. They're trying to leak it to us, but it means they may be leaking it to others as well. And when we get to a future state where we have this prefix list that we filter international connections on, we'd be able to apply the same logic. So in November of last year, we took a look at, we took a sample of 145 V4 prefixes that we reject today from our customers, not international networks. And 37% of these prefixes, when we pinged addresses within these prefixes, the ping return came over commodity. And that's 5 times higher, roughly. If you recall, globally, about 8% of these networks local pref commodity. But this rate was 5 times higher. And based on looking at the individual cases, it was pretty clear that most of these were route leaks. So this is a way to detect route leaks that you may not see because these networks are not participating in something like route views or RIPE-RIS. We also would like to detect RNE routes leaked into the commodity. And again, if we're if we're essentially pinging every prefix in the network, and we ping a prefix that we're accepting, and that comes over RNE, we ping a prefix we're not accepting, sorry, and it comes back over RNE, then it's likely that somebody is leaking a route, an Internet 2 route or an RNE route, into an environment where there's mixed routing. So another case is a member announces an Anycast prefix into RNE. You might attract traffic really not destined for that Anycast instance. So there's a census. University of Trente publishes, I think, a daily census of Anycast routes, and I think they use the K2ARC infrastructure to discover addresses that appear to be Anycast. And we use that same ARC infrastructure to find responsive, to ping responsive addresses within those Anycast, likely Anycast prefixes. And we focused on 70 Anycast prefixes that are in the RNE routing table. And so what we're trying to get to is, just like if you leak a commodity route, a non-RNE route into the RNE infrastructure, and people local pref it, they're going to do something inappropriate. Well, Anycast is the same way. It defeats Anycast. You're using Anycast so that the network finds the shortest path to that service. And if you leak an Anycast network into the RNE infrastructure, and everybody's local prefing those routes, then you can defeat that. So here's a particular pathological example. Here's an APNIC DNS server, and you can see the median ping time from the RNE network is 200 milliseconds. So this is being leaked from RNet. And I say leak, that's really not the best way to put it. There are instances where it's good to distribute these Anycast routes. What happens is, if that policy is mixed, if you don't do that for all Anycast routes, or they're not pervasive deployments of Anycast. But in this case, the round trip time is 4 times as long for the higher performance network connection, because it's ignoring an instance that's available on the East Coast. So it's traveling across the Pacific instead of taking a shorter path to get to this destination. So in summary, RNE routing is unique because, for the most part, RNE networks set a higher local pref for routes they learn from other RNE networks. We did some research to see if that was true. It is true. And then we used that research to inform a project to build an infrastructure to try and mitigate those effects. We're also doing some other things. We built an RPKI role planner that's similar to Cecilia's. And we're going to be delivering a set of tools, not just for the Internet 2 community, but we hope these tools will be of use globally. So that's it.
Thank you, Steve. I did hear you say APNIC and RNet, and I'm wondering if Jeff is going to come to the microphone. Has he been? Okay.
Correct. You're right.
You've given him something to work on.
Whoa! Can you get up at the microphone?
We get it on record that Steve is right.
No, of course you're correct. APNIC does have commercial contracts and so on to actually do Anycast, but that doesn't mean that in those other locations, and in particular the one on the East Coast, that means that we're well connected into the RNE infrastructure at that point in time. So you're picking out an RNE path. We peer directly with RNet in Brisbane. The path goes across the Pacific. And it's unfortunate because, we went and bought Anycast to provide better service to everyone, but the routing situation in RNE, as you point out, has some peculiarities which are not in the general commodity networks. And so this is one of those artifacts. But you are right, Steve. Well done.
He's going to be insufferable now, Jeff. Are there any more questions? Anything online, Sergey? All right, you get off easy then. Thank you, Steve.